In this set of problems, we are going to learn how to write precipitation reactions and how to balance them, of course. Let's take a look at the first example. I am given calcium chloride and mixing it with sodium carbonate. In precipitation reactions, what happens is you have a double displacement where I take my positive ions, which are my metals, they're written first, and I swap their places. Therefore, I pair here, I have the sodium paired up with a carbonate and calcium with a chloride. As they're on my product side, I will flip my metals. So I'll take my sodium and I'll pair it with the chlorine, and I'll take my calcium and I'll pair it with my carbonate. For these types of reactions, it's very important that we look at charges because we want to make sure that the products that we write are actually neutral compounds. Well, let's take a look at the charges on these ions. We know that chlorine, always start with a negative ion. It's going to be easier. We know that the chlorine is it's a group 7 element. Those elements will always form a -1 ion. Therefore, I will have a -1 charge on the chloride. Calcium is a group 2 element, which means that we'll always have a 2+ charge. Notice that the way it's written is balanced because I have 2 chlorides. 2 times -1 makes -2, and I'm good. Let's take a look at this example. I have CO3. Carbonate is a 2- anion, always a 2-. Sodium is a group 1. It will always have a +1 charge. Always, will never change. I've seen the tendency of students to change the charges when they write the products of precipitation reactions. Do not change the charges. The charges don't change. You will have to mess with the coefficients or the subscripts to actually make neutral compounds. This is also neutral because I have 2 sodiums, each a +1, giving me a 2+ and a 2- that makes it as 0 overall charge. Now I said I'm swapping my positive ions, therefore I will have calcium paired with carbonate here as a product. So let's write calcium and carbonate, plus I'll have sodium and chlorine. Sodium and my chloride, NaCl. Let's take a look and make sure that they are neutral compounds as written. Carbonate is a 2-. Calcium, we said it's a 2+. The charges do not change on either side. Sodium is a +1. Chlorine is a -1. These are precipitation reactions. Therefore, the charges will stay the same. We're not talking about redox reactions when they change, but here in this case, the charges remain the same. Therefore, the way I have them written is they're neutral compounds. Now is when you either have to memorize the solubility rules or really learn how to use the solubility rules in the table that's provided for you. The rules state that carbonates are insoluble, and therefore, because they're insoluble, that means that this is going to be my precipitate. Anything that has a group 1 ion, which means sodium, potassium, lithium, cesium, etc. So group 1 elements, those metals, any salt or any ionic compound that will have those group 1 metals will always be soluble. So this will, if I have this in water, is going to split apart into sodium ion, Na+ and Cl-. The halogens, so group 7, are also, so anything containing group 7 ions are also soluble. So this is double soluble, if you will, from the metal and the non-metal are both very soluble. So this isn't my precipitate. When I go to the solubility rules table and I look at the carbonates, carbonates are insoluble. In fact, the higher the charge on the anion or the cation, but the higher the charges get, the less soluble the compounds get. So this is going to be my precipitate, and I note that by putting an S for solid. Now I can take a look and see, am I balanced? Okay, I have one calcium here, one here, one carbonate, but I have one sodium here and two here, one chlorine here and two there. Therefore, to balance it out, I can put a 2 in front of that and make it. Do not put the 2's down here because we use the smallest whole number ratio between sodium and chlorine, which is 1 to 1, to manipulate the numbers on to basically to balance the whole chemical reaction. We use coefficients in front of the molecules. And now I'm balanced. Let's take a look at this example over here. I have silver nitrate. Nitrate is a -1. Silver is a +1. It's a transition metal, but it's one of those exceptions that will always have a +1 charge. Potassium is a group 1, therefore it will have a +1 charge all the time. The phosphate group, PO4 here, always has a 3- charge. Therefore, the way they are written, they're neutral compounds, because I have 3 times 1 plus 3 minus 3 is 0. Once again, what I'm doing here, I'm taking the positive ions and I'm swapping places. Therefore, my potassium will now match, will be written with my nitrate, so we can go ahead and write that, KNO3. Remember, the nitrate is a -1 ion. The potassium is always a +1. The charges do not change. They're still the same. Therefore, the way it's written, it is a neutral compound. I don't need to mess with the subscripts. Okay, now let's take a look. I have PO4 and I have silver. So I write silver. Remember that the metal is written first, silver phosphate. Okay, and we said the charges do not change. So I have a 3- charge on my phosphate, but I only have a +1 charge on my silver. Therefore, to make this a neutral compound, I need 3 silvers. So I put a 3 by my silver there, and now I have a neutral compound. Now that I have neutral compounds, I can take a look at the whole chemical reaction and figure out if I am balanced or not, which I know I'm not because I have 3 potassiums here, 1 here, and I have 3 silvers here and only 1 here. So I can put a 3 in front of this potassium, which means that I now have also 3 nitrate groups as well. So 3 nitrates, 3 silvers. I have 1 of each here. If I put a 3 in front of silver nitrate, I have balanced my silver and my nitrate groups. I'm balanced. And now I need to determine which is my precipitate. If you go to the solubility rules table, it will say that group 1, those ionic compounds that contain group 1 metals like potassium, or those ionic compounds that contain nitrate as an anion are very soluble, are always soluble, and therefore this is a very soluble compound, just like sodium chloride. Double whammy here. However, phosphates are not soluble. They're insoluble compounds, and therefore silver phosphate is my precipitate. Let's take a look at this example. I have silver nitrate again, but with potassium chloride this time. Now, let's look at the charges. We already did this here, +1, -1. Potassium is a +1. Chlorine is a group 7. It's always -1. I have neutral compounds. Now I swap positive ions, and I have potassium nitrate. The charges do not change. I have a -1 and a +1. Plus, now I paired up silver and the chloride. Therefore, here's my silver and my chloride. Silver is a +1, chloride is a -1. And therefore, the way it's written is a neutral compound. I am balanced because it's a 1-to-1 ratio everywhere. And the last part I need to figure out is which one is my precipitate. as we mentioned in this problem, KNO3 is not going to be my precipitate because potassium is a group 1 metal, NO3 nitrates are very soluble, therefore this isn't my precipitate. I have to look at my other ionic compound. Chlorides in general are soluble, but for a few exceptions, and one of those exceptions is silver. Silver chloride is not a soluble compound. Silver chloride, lead is another one, and there's a few more, but chlorides in general are soluble, but when they're paired up with ions such as silver or lead, you can look at the exceptions in the solubility rules, they are not soluble. So silver chloride is not soluble. It's my precipitate. Let's take a look at the next example. I have lead nitrate plus sodium chloride. And I have missed a 2 here. Lead nitrate, lead 2 nitrate plus silver chloride. Let's make sure that we have the correct charges. We said that NO3 always has a -1 charge. Now the charge on the lead, it's easier to start with a negative ion because we have positive ions or metals that don't always form, they form multiple ions, and therefore if I just looked at the lead, I wouldn't be able to necessarily say it's a +2 or a +4. But if I look at what it's paired up with, I look at the total negative charge, that will tell me the charge on the lead. So let's take a look here. My nitrate is a -1, and I have 2 of those. Therefore, my total negative charge is -2, and my total positive charge has to balance it. It has to be a +2, and because I only have 1 lead, it will be a +2 ion. Now let's take a look here. Sodium is always a +1 because it's group 1. Chlorine will be a -1 ion because it's group 7. And now I'm going to swap ions. Let's start with sodium. Sodium will be paired with a nitrate. Sodium is a +1. The charges don't change. And a -1, this is a neutral compound. I don't have to mess with it. And then I have to pair up the lead with the chlorine or the chloride. So I have lead chloride, lead 2. The charge on the lead we said was 2+, and it doesn't change, so it's a 2+. Chlorine is a -1. To make this a neutral compound, I need 2 chlorines, and therefore I put a subscript 2 by the chlorine. Now let's take a look and make sure that we are balanced here. We have 2 nitrate groups, but only 1 here. We have 2 chlorines, but only 1 here. Therefore, if I put a 2 to balance my chlorine in front of the sodium chloride over here, 2 chlorines, 2 chlorines. I have 2 sodiums now, but only 1 here. 2 nitrates, but only 1 here. Therefore, if I put a 2 in front of sodium nitrate, that balances the whole equation out. Then the last thing I need to figure out is which one is my precipitate. Once again, it's not going to be sodium nitrate. Sodium is a +1 ion. Therefore, it will always be soluble. So ionic compounds that contain sodium are always soluble. Ionic compounds that contain nitrates are always soluble. Therefore, whichever ion you look at, this is going to be soluble. We said up here that chlorides are typically soluble, but if they are paired with lead or silver, then they are not soluble. Therefore, this is going to be my precipitate. I write an S for a solid. Let's take a look at our last problem of this type, and then we're going to erase it, and then we go to the second set of problems where we actually have words and we have to translate those into formulas. We have iron 2 sulfate and magnesium nitrate. Sulfate has a 2- charge always. Therefore, my iron here has to have a 2+ charge to balance it out. That's why it's iron 2 sulfate. Iron can also be a 3+ ion. Now let's take a look here. Nitrate, we said, has a -1 charge always. I have 2 of those, which means that I have a 2- charge. Magnesium is a group 2 ion. It will always have a 2 plus charge. So I have a 2 plus and a 2 minus. This is neutral the way it's written. Now once again, I swap ions. So I have magnesium sulfate, and then I have iron 2 nitrate. Now let's take a look and make sure that they are neutral compounds. The sulfate charge does not change. It's a 2 minus charge. Magnesium charge does not change. It's a 2 plus. 2 plus, 2 minus, this is neutral. I don't need to mess with it. Iron, we said, is a 2 plus ion. Nitrate is a -1. And therefore, to make this a neutral compound, I need 2 nitrates, each with a -1 to give me a 2 minus. The way it's written now, but with that 2 subscript, it's a neutral compound. Let's take a look and make sure that we are balanced. We have one magnesium, one sulfate group here, one sulfate group here, one iron, 2 nitrate groups, 2 nitrate groups. The whole chemical reaction is balanced. And lastly, let's figure out which is my precipitate. Well, if you look at the rules of the solubility rules, sulfates are actually soluble except for calcium or barium, etc. But magnesium sulfate is not one of those exceptions, which means that magnesium sulfate is soluble. When we take a look at the next compound, we see that we have a nitrate for an anion, and we said that any of those ionic compounds that have nitrates as an anion are always soluble. Therefore, this is also soluble, which means that this reaction does not give me a precipitate. And if you were asked to figure out the precipitate, you would say no precipitate occurring for this reaction. Everything is soluble. Okay, well, we'll pause here, we'll erase, and then we'll continue on with the second set of problems.